All right, so some homework problems on eigenvalues in the spectrum of a matrix.
Yes, Professor, can you like problems like 6 or 7, please?
Okay, let's take a look. So this is number 6 on spectral theory, eigenvalues. So we have T, the linear operator from V to V, and T of V is lambda V. So V is an eigenvector, the eigenvalue lambda, and T of V is also equal to mu V, right? So that means that lambda V equals mu times V, because they're both equal to T of V, which lambda minus mu times V is 0. So if a scalar times a vector is 0, either the scalar is 0 or the vector is 0. But the vector is not 0. So lambda equals mu. Right. Let's see. See, why is it the case that lambda minus mu has to be 0? So it's certainly true. Lambda V equals T of V equals mu of V. So this is correct. So if you bring this over to the other side, lambda minus mu is 0. Let me just make this note. If lambda minus mu is not 0, then 1 over lambda minus mu is perfectly good number. So 1 over lambda minus mu times lambda minus mu V is 0, but 1 over lambda minus mu times lambda minus mu, that's just 1. This is just V. So V would be 0. So, but V is not 0. So it has to be the case that lambda equals mu. Questions about that? Let's see. Let's look at number 9, random. Let's see. So we have a linear operator T from V to V. So you can compose this. Right, so if you have an operator from T to a space, V goes to V, and then goes to apply V again, apply T again, that would be the operator T squared. And if you compose that with T again, that would be the operator T cubed and so forth. So given an operator T from a vector space to V, we have T composed with itself any number of times. So we have the operator T to the power R from V to V, right? That just means T composed with T composed with T sometimes. So we say that T is nilpotent if T to the R is 0 for some positive integer R, right? Nilpotent to the 0 power. So, or a certain power is 0.
Professor.
Right?
Professor.
Yes, sir.
What do you mean by non-potent?
I just defined it. T is nilpotent if T to the R is 0 for some positive integer R. This is the definition.
Okay.
Right?
T to the V. Okay. Thank you.
So suppose lambda is an eigenvalue for t. So that means t means that there exists a non-zero vector such that t of v is lambda v. So if you look at t squared of v, what is t squared of v? T squared means t of v. So that's t of lambda v, which is lambda t of v, because t is a linear operator, which is lambda times t of v is lambda v. That's lambda squared v. So t squared of v is lambda squared v. And what's t cubed of v? This means t of t squared of v. T squared of v is lambda squared v. So this is t of lambda squared v. You can always take a scalar outside. That's lambda squared times t of v. T of v is lambda v, so that's lambda cubed v. And in general, t to the r of v will be lambda to the power r times v. On the other hand, t is nilpotent, so t to the r is 0. Right? So I have a non-zero vector times lambda to the r is 0. So lambda to the power r is 0, which means lambda is 0. So that's the proof. That's the solution to exercise 9. The only eigenvalue of a nilpotent operator is 0. Any questions about this?
So Professor, for that one, lambda is going to equal to 0, right?
Why?
It's going to be equal to 0.
Yeah, that's what you have to prove. Lambda equals 0.
Okay. Can you explain the last line?
Excuse me?
Can you explain the last line?
This?
Yes.
Well, if you have a number and you raise it to the power r and you get 0, the number has to be 0.
Okay.
If you take any non-zero number and you multiply it by itself as many times as you want, it's never going to be 0.
Yes. All right. I got it. Thank you.
Okay. Let's look at problem 10. So if you have a linear operator from v to v, and let's see, let lambda be a scalar f. So if you look at the set of all the vectors in the vector space, such that t of v is lambda v, this is what I called E of lambda. And so this includes the vector 0, because t of 0 is 0. And it includes every eigenvector. So this includes all eigenvectors. With eigenvalue 0. And this is a vector subspace of t. So it has a dimension, and the dimension of E of lambda, if it's just the 0 subspace, it means lambda is not an eigenvalue. The dimension of this subspace is 1 if and only if lambda is an eigenvalue. It means it has a non-zero eigenvector. and what is called the geometric multiplicity of lambda is the dimension of this eigenspace E of lambda. That's the definition of geometric multiplicity. So in problem 10, we have a linear operator from V to V. V is a vector space of finite dimension n, and suppose lambda is an eigenvalue with geometric multiplicity n. That means this eigenspace E of lambda, which is all the vectors in V, such that T of V is lambda V, the dimension of E of lambda is n. Right? Or suppose the dimension of E of lambda is n, the geometric multiplicity is n, but that's also the dimension of the vector space. So you have a subspace of a vector space of the same dimension. That means E of lambda equals V, which means T of V is lambda V for all vectors in the vector space. Which means the operator T is exactly lambda times the identity. T of V is lambda times the identity times V for all V. T is the identity times, is the eigenvalue lambda times the identity. And if T were the lambda times the identity, then every vector would be an eigenvector for the eigenvalue lambda, and so E of lambda would be the whole vector space. So this is really just understanding the definition of geometric multiplicity. Right? Should I do any more of these?
Yeah, Professor, number 11, please.
So so T is a linear operator from the vector space V to itself. With distinct eigenvalues,
Right, okay.
lambda 1 up to lambda k.
Be distinct value of T.
And if you take the eigenspace E of lambda I, that has some dimension, say it's D sub I, and so let's grip B sub I be a set of vectors VI1, VI2, up to VI
Yeah.
D sub I. This is a basis for the eigenspace E of lambda. And I want to show, this is the exercise, that if I take the union of these sets of vectors is a linearly independent set of vectors. So how do we prove this? Well, so suppose some linear combination of these vectors is equal to 0. So suppose we have scalars such that summation I goes from 1 to k, and then for each I have summation j goes from 1 to d sub I, Cij v sub I d sub j is 0, right? So this is a vector in b sub I, and this is the sum of these vectors, okay? So I must show Cij equals 0 for all I and j. Well, in fact, suppose I call this vector Wi, is this vector Cij vi d sub j, j goes from 1, sorry, Vij, Cij Vij, j goes from 1 to d sub I. This is a vector in E of lambda I, right? So again, you have to sort of keep track of what's going on. I have a linear operator. I choose k distinct eigenvalues. Each eigenvalue has an eigenspace. There it is. Its dimension of the eigenspace for the vector lambda I is d sub I. That's the dimension. That's the geometric multiplicity or the dimension of this eigenspace. So this vector subspace has a basis consisting of d sub I vectors. So I take all of these together for all the different eigenvalues. So I have k of these spaces. So I have a lot of vectors, and I suppose some linear combination of them is 0. But this linear combination is really a sum of I goes from 1 to k. This is some vector Wi. So this is summation Wi equals 0. I goes from 1 to k. But the set of vectors W1, W2 up to Wk is linearly independent, because one of the theorems about eigenvalues is that if you so Wi is an eigenvector for the eigenvalue lambda I. And if you take different eigenvalues and you take an eigenvector for each of them, that set of vectors you get is linearly independent. So the only way a linear combination of these vectors can be 0 is if, in fact, these are all the 0 vector, right? These can't be non-zero. So W sub I equals 0 for all I. And Wi is summation Cij Vij. J goes from 1 to d sub I. If this is 0, these vectors are linearly independent because they're the basis for a certain eigenspace. So Cij equals 0 for all I and j. And that's the proof. So it uses the fact that a linear combination of these vectors is, if you group the terms properly, it's a linear combination of vectors in each of these spaces, E of lambda I. And eigenvectors for different eigenvalues form always a linearly independent set. Okay.
Professor,
Yes,
you said they are always linearly independent?
so what I said is the following. So you have T from V to V,
Mhm.
and lambda 1 up to lambda K
Yes.
are distinct eigenvalues,
Mhm.
and V1 up to Vk are eigenvectors such that T of the vector Vi is lambda sub I times V sub I. So I have distinct eigenvalues, an eigenvector for each of them. Then this set of vectors is a linearly independent set.
Okay.
And let me just show you the proof. In this case, K equal 2. So we have lambda 1 different from lambda 2, two different eigenvalues.
Mhm.
T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2. So suppose C1 V1 plus C2 V2 is 0. I want to show C1 equals C2 is 0. But T of C1 V1 plus T of C2 V2, that's C1 T of V1. So T of C1 V1 plus C2 V2, that's T of C1 V1 plus T of C2 V2, that's C1 T of V1 plus C2 T of V2. T of V1 is lambda V1 V1, and T of V2 is lambda 2 V2. But this is the 0 vector, so this equals 0. So I have this linear equation. I also have this linear equation. Let me multiply this equation by lambda 2. I get C1 lambda 2 V1 plus C2 lambda 2 V2 equals 0. When I subtract, these cancel. I get C1 lambda 1 minus lambda 2 V1 is 0. So this vector times this number is 0, but lambda 1 is different from 0. This is different from 0.
Yes.
So the only way this can be 0 is if C1 is 0. And if C1 is 0, then C2 V2 is 0. So C2 is 0. So we have linear independence.
Okay. Okay.
Yeah. That's the story.
Professor,
Yes.
what about number 8?
Well, 8. T of 0 is 0 for any linear operator. So 0 is invariant with respect to T. Remember, W invariant with respect to T, where W is a subspace of V, just means that T of W is contained in W. Another way of saying that is, for every vector W in W, so here's the vector space V, here's W.
Mhm.
And if you take a vector W in here, T of W doesn't move outside of W. T of W is in capital W. That's what it means to be invariant. So T of 0 equals 0. That means the 0 subspace gets mapped to 0, means it's invariant. And T of V is certainly contained in V, so V is also invariant. So this is just a matter of thinking carefully about the definition of invariant.
Professor.
And let me do number 7. That's the last one I think.
Professor, is that number 8?
This was number 8.
If you let A be an n by n matrix, that's the question.
Sorry?
The question is, let A be an n by n matrix.
Oh, it's the same thing. So A and n by n matrix. So the operator T from V to V is defined by T of the vector V is just A times V. It's
Okay.
just another way of saying a linear operator. It has
Okay.
nothing to do with being a matrix.
Oh,
I mean, I say A and T. I could have said it's invariant with respect, but I understand there's an ambiguity there. But it just means A is, there's nothing, a linear operator is just an n by n matrix.
okay. Amen.
In problem 7, 0 is an eigenvalue if and only if there's a vector V different from 0 and T of V is 0 times V, which means the 0 vector, which is true if and only if V is a non-zero vector and V is in the kernel of T, which is exactly the same as saying that the kernel of T consists of more than the 0 vector. Okay. All right. Let me begin the discussion of inner product spaces. So you know, for example, in the vector space R2, you can have a vector, and we talk about its coordinates that say x, y. But in addition to just what we've been discussing about the operations of in a vector space of vector addition and scalar multiplication, in R2, vectors have length and they have directions. And you can talk about, for example, 2 vectors being perpendicular. Or you can talk about the angle between 2 vectors. And up to this point, we don't have a language or a tool for doing that. But I want to bring this simple geometry into our linear algebra. And so let me just say, I want to define an inner product. So I just want to consider now vector spaces over the field of real numbers. So an inner product on V, a vector space, is a function from V cross V into R. That means it's a function that assigns a number, a real number, to every ordered pair of vectors. Right? So So f of VW is some number. And instead of using f to denote the function, it's traditional to denote this function. Instead of writing f of VW, just write v comma w. This is going to be our notation for the inner product of two vectors. So given any pair of vectors v and w, this function assigns some real number. And I want to say what properties this has. So VW, first of all, is what is called bilinear. And that means the following. If I take V1 plus V2 comma W, that's V1W plus V2W. And a scalar times V, inner product with W, is C times VW. And similarly, with respect to the second coordinate. So I want this inner product to be bilinear. I also want it to be symmetric. That means the inner product of V and W is the same as the inner product of W and V. And the third property is that the inner product is what is called positive definite. That means the inner product of V with itself is always a strictly positive number if V is not zero. So an inner product on a real vector space is a function that assigns a number or a scalar to every ordered pair of vectors. And this function is bilinear, it's symmetric, and it's positive definite. And when one says Euclidean space, this means some real vector space with an inner product. Okay, this is just the definition. And the one that you know from calculus is R2 with the dot product, which is also called the scalar product, which is the inner product. And it's defined as follows. If V is the vector x1, x2, or x1, y1, v1, and v2 is the vector x2, y2, the inner product of v1 and v2 is x1, x2 plus y1 times y2. Right? So you can't take linear algebra, I think, without Calc 3. So you have to have seen this already. If you haven't, it doesn't matter. I mean, I'm defining it for you right now. In general, in Rn, what is often called the standard inner product, if you take V to be the vector x1, x2, x3 to xn, and W to be the product, the vector y1, y2 down to yn, the inner product of V with W is x1, y1 plus x2, y2 plus x3, y3 up to xn, yn. Maybe I should have written this as x1, x2, and this says y1, y2, and then this would be x1, y1 plus x2, y2. But this is the standard inner product in the n-dimensional vector space Rn. Right? And to check that this satisfies the properties isn't very hard. For example, what's the inner product of a vector space with itself? In that case, x1 equals y1, x2 equals y2, and so forth. This is x1 squared plus x2 squared plus xn squared. And that the only time that equals 0 is when all of the scalars are 0, which means exactly that the vector v is 0. So you see immediately from the definition that this inner product is positive definite. Let's take another example from calculus. Suppose we have the interval from a to b, and we look at all functions, and this is CAB, is all functions f, real valued functions that are continuous. So they teach you in calculus that the sum of continuous functions is continuous, so this is a vector space. And we define the inner product of two functions, f and g, to be the integral from a to b of their product. So for example, the inner product of g and f is the integral from a to b of g of t, f of t, dt. But g of t, f of t is the same as f of t, g of t. So that's fg. That says that this inner product is symmetric, this function is symmetric. What's the inner product of f with itself? It's the integral from a to b of f squared of t dt. The only way this is equal to 0 for a continuous function is f of t equals 0 for all t. So this is positive definite. If we take, for example, f1 plus f2 inner product with g, that's the integral from a to b of f1 plus f2 times g dt. That's the integral from a to b of f1g plus f2g dt. And the integral of a sum is the sum of the integrals. So this is f1g plus f2g. So this is another example of an inner product. Now, let's just motivate something. Suppose we're in R2, and here's the vector x1, x2. Call that v. So this is x1, this is x2. The length of the vector v, which I'll write as v with double borrows around it, this is x1, this is x2. That's the square root of x1 squared plus x2 squared. That's just the distance formula in the plane, which is the square root of, this is the inner product of v with itself. Right? The inner product of v with v is x1 squared plus x2 squared. So in general, in any inner product space, you define the length of the vector v as follows. The length of v is defined to be the square root of the inner product of v with v. That's the definition. So once you have an inner product space, you can define the length. And we say v is a unit vector in v if its length is 1. So a unit vector is just a vector of length 1.
Excuse me, Professor, can you move the paper a little bit to the left so we can see the whole thing? Thank you.
Now, if we take the inner product of CV and CV, so V is a vector and C is a scalar, because this is bilinear, this is C times the vector times the inner product of V and CV. I just pull this out, and I can pull this out. I get C squared, the inner product of V with V. And this, the inner product of vector with itself, that's the square of the length. So if I take the square root, the length of CV is the square root of this, which is square root of C squared is the absolute value of C times the length of V. So this is just a sort of obvious statement. And if you take any vector W different from 0, then the length of W is positive. Of course, the inner product of W with itself is positive. That's positive definite. So if I take the vector 1 over, this is a number, 1 over the length of W times W. What is the length of that? I can take this outside, that's 1 over the length of W times the length of W, which is 1. So W divided by its length is always a unit vector. So what I've just shown is defined really is the inner product determines length. That is, the length of a vector V you get from the inner product by taking the inner product of v with itself in the square root. So if you know the inner product, you can define the length of the vector. But it's also true, this is the first theorem in this chapter, is that length also determines the inner product. So if you know the if you suppose you know the lengths of every vector, if you want to find the inner product of two vectors, v1 and v2, this is 1/4 the length of the sum of the vectors squared minus 1/4 the difference of the vectors squared. For all vectors v1 and v2 in the vector space. So how do we prove that? Let's see. The length of v1 plus v2 squared, that's the inner product of v1 plus v2, v1 plus v2. If you expand this by bilinearity, this is v1 comma v1 plus v2 plus v2 comma v1 plus v2. If you expand this by bilinearity, this is v1 v2 plus, v1 v1 plus v1 v2 plus, inner product of v2 with v1 and the inner product of v2 with v2. And by symmetry, v1 v2 and v2 v1 are equal. So this is the length of v1 squared plus 2 times the inner product of v1 and v2 plus the length of v2 squared. So the length of v1 plus v2 squared is equal to this. And if I wanted to calculate the length of v1 minus v2 squared in terms of the inner product, I would have minus signs here. And I would end up with v1 squared minus 2 v1 v2 plus v2 squared. And if I were to subtract the second equation from the first equation, I would get v1 plus v2 squared minus v1 minus v2 squared equals, these cancel and these cancel, and 2 minus minus 2 is 4 v1 v2. And if I divide by 4, I get exactly this. So this is something called the polarization identity, but it simply tells us that if you know the lengths of vectors, you can use them to define an inner product. Now, very often on a vector space, you have a linear operator on an inner product space. An inner product space just means a vector space in which there's some inner product that's been defined. and we say T is an orthogonal operator, if it preserves the inner product. And what that means is that if I take vectors v and w, the inner product of t and v and t of w is the same as the inner product of v with w for all v and w in the vector space. And geometrically, these are very nice operators because they don't stretch anything. They preserve length. So this is really theorem 2. An operator T from V to V is orthogonal if and only if T preserves length. What that means is if I take any vector V and apply T to it, and I compute the length of T of V, that's exactly the same as the length of V. So it moves an operator, it moves a vector, but it doesn't stretch it in any way. So for example, if this is the vector V, the set of all vectors which have the same length as V lie on this circle, and T of V would have to be some vector that goes to that circle because the length doesn't change. So an orthogonal vector, an orthogonal operator can rotate a vector, but doesn't stretch or contract it in any way. So the proof, well, let's just show that orthogonal operators preserve length. That means, what is the length of T of V? If I square that, the length of T of V is just the inner product of T of V with T of V. But T preserves the inner product, so that's the inner product of V with itself, and that's the length of V squared. So if I take the square root, length of T of V equals the length of V. So an orthogonal operator preserves length. On the other hand, if T preserves length, then the identity I discussed a moment ago, which I said was called the polarization identity, says what? Polarization identity says that you can express the inner product T of V1 and T of V2 in terms of the lengths of some vectors. It's 1/4 T of V1 plus T of V2 squared minus 1/4 T of V1 minus T of V2 squared, which is 1/4 the length of T of V1 plus V2 squared minus 1/4 the length of T of V1 minus V2 squared. But if T preserves length, the length of T of V1 plus V2 is the same as the length of V1 plus V2. And similarly for the difference. And again, by the polarization operator, this is exactly the inner product of V1 and V2. So if an operator preserves lengths, it also preserves the inner product, and that means it's orthogonal. Let's see. In R2, what's the simplest orthogonal operator? It's a rotation. So consider rotation by theta in R2. That takes any vector V this is r sub theta v. This is the vector you get by rotating by theta. And if I wanted to represent this rotation by a matrix, let me just call it T. T of xy is cosine theta sine y minus sine theta, sine theta, minus sine theta, cosine theta. So this is the matrix for a rotation. Oops. Sine theta, sine theta. Right. This is the matrix for rotation by an angle theta. So let me just multiply this out. So T applied to xy is cosine theta sine theta minus sine theta cosine theta applied to xy. This is x cosine theta minus y sine theta, x sine theta plus y cosine theta. So what is the length of the vector T of xy squared? It's this squared plus this squared. It's x cosine theta minus y sine theta squared plus x sine theta plus y cosine theta squared. If I just do my arithmetic, square this, x squared cosine squared theta minus 2xy cosine theta sine theta plus y squared sine squared theta plus x squared cosine squared theta plus 2xy cosine theta sine theta plus y squared cosine squared theta. When I add, these cancel. I get x squared cosine squared. Oops, sorry, this was a sine. I get x squared cosine squared theta plus sine squared theta. These cancel. Y squared sine squared theta plus cosine squared theta. These are 1. So this is x squared plus y squared. So this is exactly the length of the vector xy. So this rotation by an angle theta preserves lengths. And so that's a very nice example of an orthogonal operator. We'd like to also figure out a way. I just described how to measure the length of a vector in a product space. What about the angle between two vectors? We'd like to have some way, given vectors v and w, to define the angle between v and w. So first, let me define parallel. Suppose I have two non-zero vectors. Non-zero vectors v and w are called parallel if one is a scalar multiple of the other. W is c times v. for some scalar c. And perpendicular if the inner product of the two non-zero vectors is 0. So this is a definition of parallel and perpendicular, and a synonym for perpendicular is orthogonal. So two vectors are orthogonal means the same as perpendicular. A set S of vectors is orthogonal, set S of non-zero vectors, if every pair of them are orthogonal or perpendicular. So the inner product of V and W is 0 for all V and W in S, V different from W. And we say S is orthonormal if S is orthogonal. So S is a set of non-zero vectors that are mutually perpendicular, and they all have length 1. The length of V equals 1 for all vectors V and S. So these are basic notions in the geometry of vector spaces. What it means for two vectors to be parallel, what it means for two vectors to be perpendicular. One is a set of vectors orthogonal and one is a set of vectors orthonormal. And there's a nice connection between an orthogonal set of vectors and a linearly independent set of vectors. So let me just write it down. This is a little lemma. An orthogonal set of vectors is always linearly independent. Proof. Let S be some orthogonal set. And suppose I have vectors V1 up to Vk, different vectors in S. Suppose C1 V1 plus C2 V2 up to CK Vk is 0. Some linear combination of these vectors is 0. Must show Ci is 0 for all I. Let me just show that C1 is 0. The argument is the same for all of them. So suppose I take the inner product of V1 and this vector. On the one hand, this vector is 0, so this is V1 inner product with 0. And the inner product of any vector with 0 is 0. But on the other hand, by the bilinearity, this is equal to C1 V1 comma V1 plus C2 V1 comma V2. If I kept going, I would get C3 V1 comma V3 all the way up to CK V1 comma VK equals 0. But these vectors are orthogonal. So the inner product of any two different ones is 0. So these are all 0. And I'm left with C1 times the length of V1 squared equals 0. This is not the 0 vector, so the length is not 0. So if the product of two numbers is 0 and one of them is not 0, then C1 is 0. And in this expression, if I had taken the inner product of this linear combination with the vector vi in exactly the same way, I would get that Ci is 0. So orthogonal implies linear independent. By the way, when I mentioned orthonormal set of vectors, recall the standard basis in Rn, you have vectors E1 up to En, where Ei is the vector which all zeros, a 1 in the ith place, and then all the rest are zeros. So if I take the inner product of Ei and Ej, for I different from j, I'll get, so here I have one vector. My other vector is zeros and a 1, but it's in a different place. I'm just going to get 0. The inner product, for example, if I take 1, 0, 0 and 0, 1, 0, the inner product is 1 times 0 plus 0 times 1 plus 0 times 0, which is 0. These are all 0. Phi is different from j. And if I take the inner product of I with itself, I get 0 squared plus 1 squared plus 0 squared. I just get 1. So the length of Ei squared is 1. So the length of Ei is 1 for all I. So for the standard basis in R2, the vectors are orthogonal. They're mutually perpendicular, and each, so that's an orthogonal set, plus each vector has length 1. So it's an orthonormal set. Now, I could be doing all this over complex vector spaces as well, but I think I'm just going to talk for the moment about real vector spaces. Let V be an n-dimensional vector space with an orthonormal basis E1 up to E sub n. So that means the inner product of Ei and Ej is equal to, that's right, delta Ij. This is 1 if I equals j and 0 if I is different from j. And this symbol, which we use in number theory and algebra and linear algebra and everywhere else in mathematics, it's called the Chronicler Delta, after a German mathematician named Chronicler. So in an orthonormal basis, the inner product of two different vectors is 0, and the inner product of a vector with itself is 1. Then, if V is the vector summation xi ei, and W is the vector summation yi ei, then the inner product of V and W is exactly the familiar inner product x1 y1 plus x2 y2 up to xn yn. And the proof is that the inner product of V and W, V is summation xi ei, I goes from 1 up to n, W is summation, all right, of yj, ej. J goes from 1 up to n. When I expand this by bilinearity, I get a sum over all I and j from 1 to n, xi, yj, in a product of ei and ej. But this is 0 except when I equals j, and then it's equal to 1. And when I equals j, you just get summation xi, yi. I goes from 1 up to n. This is the standard inner product, x1, y1, x2, y2, up to xn, yn. So I'm not going to go through it now because I think it's a lot of work now for you to try to understand these various concepts. But in every inner product space, from every basis, we can construct an orthonormal basis. So these orthonormal bases, which allow us very easily to calculate the inner product, there's something called the Gram-Schmidt orthogonalization process that from a given basis allows us to construct an orthonormal basis. And I guess that's the first thing that we'll do when we come back from our spring break. All right, so that's a fair amount that we've done today because we're introducing a new subject, a new concept. I mean, it's not really new. You learned this a long time ago, that things have length, and if you have two things, you can talk about the angle between them. But now we're going to be able to extend these very concrete notions to abstract vector spaces that have an inner product. And the notes online, and a good way to spend the spring break is by studying inner product spaces. All right, any questions before we stop for the morning?
Professor,
Yes, sir.
is there a review for the second exam?
Sorry, what?
Do we have any review for the second exam?
Well, there will be.
Okay,
I'll actually try to send out a review this weekend, so
okay,
you have a chance during break to study it.
okay, cool.
But when we come back from the break, there still are 2 weeks until the exam.
Okay,
But there will be a review, and I'll try and get it out this weekend.
okay, thank you.
Sure.
Have a good evening.
Any other comments or questions? If not,
Have a good one,
Supposed to-
Professor.
it's supposed to be very nice today, so hope everyone gets to enjoy the day and enjoy your break. Bye, everyone.
All right.